Hello, welcome to this session. I'm going to give an overview of the operations and maintenance of floating offshore wind farms. It'll just give an overview of some of the key considerations. Firstly, I'd just like to say thank you very much to the organizers for the invite to present today, and I hope you find it useful. And please do feel free to contact if there are any questions. Um, my name is Dan Carl Spearman. I work for RCG, and I'm based in the London office. Briefly, RCG are an international company, so with offices across APAC, EMEA, and the Americas. And we formed in 2015 and have about 60 employees. We were actually recently acquired by ERM, and I'll touch on that kind of wider overview. So we provide services across the advisory space, and really supporting the development of offshore wind projects across the life cycle. My focus is very much on floating wind, and supporting particularly commercial scale projects through up to or pre-FID, and supporting the various activities, and from the technical through to the market and strategic advisory, as well as the transactional side for those projects. So just trying to give a bit of an overview of where we get involved, but it's very much from the early stage, typically through to FID, and then as we go on, the next stage is towards more of an owner's engineer type role. So RCG, as I said, we have a footprint internationally, but as part of the acquisition and embedment within ERM, we have a much wider footprint, where ERM has nearing 6,000 employees, and including offices in South Korea. So, very much gives us that market opportunity to support clients across those different markets. The ERM is looking to very much be the largest global pure play sustainability consultancy. So, offshore and floating wind being one aspect, but looking through the wider sustainability field. So, as mentioned, the aim of the topic here is to give an overview of the O&M aspects for floating wind. So, firstly, I wanted to give a bit of an overview. What is it we're doing with the O&M, and the key objective is, of course, to keep the turbine spinning. That's the overall objective, is to ensure the turbines are operating either as expected or above, and it's a balance of what is spent, the OPEX, versus the availability of the turbines, and that's what's quite critical. And from an O&M perspective, we have a lot of experience from the fixed bottom side, and it's applying that to where the requirements for floating offshore wind. So I'll make quite a few comparisons between fixed bottom and floating wind in terms of what we know and what we can apply directly, and what's an additional. Again, from a fixed and floating perspective, we're talking about the almost identical turbines, but it's generally below the turbine that the key differences. And very similar to fixed bottom, we have both minor interventions and major interventions, which are outlined here. So the same maintenance requirements, but the approaches need to be done in a slightly different way. So in the minor interventions, we have things like scheduled maintenance, and this is operations that's undertaken throughout the year, both planned as well as corrective. So the planned is what we're expecting to do, whereas corrective might be where there might be turbine or unexpected failures within the turbine that need to be corrected. And these are failures for smaller components, so generally up to several hundred kilos, where you can use smaller access methods. So we call this the minor interventions. This can be undertaken from vessels, so crew transfer vessels, SOVs or helicopters, and I'll touch on those in a little bit on the next slide. And this is very much similar to the approach in the fixed bottom side. However, there's a couple of challenges related to this. One being the relative motion between different vessel types and different platform types, because for fixed bottom we have a floating to fixed transfer, whereas moving to floating wind, it's a floating vessel to the floating platform transfer. So it's a more complex motion, and that doesn't necessarily mean it'll be worse, but there'll be consideration where some will be improved, some will be not such good transfer windows. So there's kind of pros and cons to that. There's also some concern around motion sickness within the floating platform, particularly with the larger turbines where you're high up in the nacelle. You can see some relatively significant motions so on the personnel. So you're inside in the nacelle with fairly potentially significant motions. So this can cause simply fatigue or can cause vomiting, which neither is productive for when you're trying to undertake the work. In addition, we have a lot more subsea components and critical, structurally critical components that both need to be maintained and inspected, compared to fixed bottom, where it is that the structural element is purely the monopile or jacket foundation. And finally, the other aspect is more relating to the unknowns of component failure rates. So although we have a track record of certain number of platforms being operational, it's a very small number compared to fixed bottom. So on the kind of multiple orders of magnitude. So there's the data and the confidence in the data in terms of what the effect of going to floating for failure rates there's not as much confidence. It has, however, been seen that from the existing units that we're not seeing excessive component failures, but the numbers of platforms means there's not sufficient data to have the confidence at this stage. Then if we move on to the right side, this is the major interventions. So this is where you need, so in the fixed bottom side of offshore wind, you would bring in jack-up vessels generally to do the operations, so to give you a stable transfer where you're jacking the vessel up and you're able to do a fixed to fixed platform, so it reduces the motions. However, with floating wind, you're in deeper waters, so you can't use those jackups. So I'll talk a bit more about this as we go through, but we're replacing things like blades or the main drivetrain components. So you're talking about heavy, large, and difficult to handle components. And so, the key challenge in this is that you need to use kind of a couple of different techniques. So either doing the operations offshore or bringing them back to port. And the challenges of doing that offshore is the motions, particularly high up between the crane vessel and the nacelle from the platform can be quite significant. It doesn't take much pitch or roll motions to have quite significant relative motion. In addition to this, particularly as we start scaling up the turbines, there's quite limited or no technology available to perform this operation offshore as well. So the availability of those vessels coming online is a challenge for doing that. And finally, there are a lot of different platform designs. So each of those different designs have some subtleties in terms of how you undertake the maintenance. So the shapes, the responses how you undertake disconnecting the mooring lines and the cables. So there's not a standardization yet for the industry. So we're diving a little bit into those different approaches and strategies for the minor interventions. We're for fixed bottom wind and for floating wind, we would expect to see kind of a similar approach in terms of using these three key strategies. But there are some key differences between in the responses or performance of these vessels. Where we see the first column is crew transfer vessels, and this has been still the predominant access method for fixed bottom wind, and it's generally up to about 30 nautical miles is the kind of the maximum you would expect those, or about 60 kilometers. And they work day shifts generally, so 12 hours in the operational or in the O&M phase. And generally there's no accommodation on board. And what we see is these are limited by wave motions, and this limits the transfer. And generally, 1.5 meters significant wave height would be roughly the limiting criteria, both for the push on. So when the vessel pushes on and uses friction on the bow, for the technicians to transfer, or for the transits. So transit being the actual steaming of the vessel out to the project. So again, if you for example, if you're talking 30 miles doing 20 knots, that's an hour and a half of transiting. So if you have quite significant motions, the technicians aren't going to be in such good fit state to work if the conditions are rough. And this is, I guess, where you come into the second option, being the service operations vessels, or SOVs. And these are getting used a lot more for the further and larger projects for two reasons. Primarily one being that they're able to operate in rougher conditions, so less downtime of the vessel, as well as there's no very much smaller transit time, because they stay offshore for 1 to 2 weeks generally before coming back to shore. So you don't, and the technicians stay on board, so there's accommodation for them to stay. So this means that you're not losing time going between the port and the project. Especially important as you get further offshore, you get a lot of lost time for transiting. And there's other benefits in having the crew in an environment where it's fully offshore. You're not going back to port, and then there could be other outside influences which affect work and safety. So a typical example would be going to the bar or to the pub. The next day you might not be so fit for work, and these elements are actually quite important when you're offshore in challenging environments. Whereas if on board the SOVs, it's very much a controlled environment, and the duty holder or the developer can ensure the well-being of the technicians, and there's it's much more regimented. So yeah, that's the SOVs, and as I say, kind of we would typically expect this to be much more adopted in floating wind compared to CTV, because we're expecting the projects to be further offshore. And I should say that from fixed to floating perspective, probably one of the key elements is, again, this relative motions. So motions in terms of the pitch and roll, where the gangway transfers, but also the watch circle, or the as the waves and the wind loadings move the platform, there'll be a certain motion of the platform, and the vessels stationing system or dynamic positioning system will have to match that motion. So there's several dynamics that need to be taken into place, which don't happen in fixed bottom. And then the final option is the helicopter, which we do see in projects, but it's less common than the SOV and CTVs. And really, it's much larger distances can be considered, as you're limited essentially by fuel capacity and the rescue cover. And the technicians themselves can also be transferred directly to the nacelle, so at the place of work. So from a kind of speed point of view, there's definitely some advantages. Interestingly, transfers are limited by wind speed, which is kind of just common sense, but wave heights also do limit the helicopter transfers, and this is actually based on rescue requirements. If the helicopter needs to ditch, it has to be wave heights where rescue vessels can get to the helicopter. And I think this is probably a key one where research is being done in terms of understanding what the relative motions are between the nacelle and the helicopter when they're winching down technicians. So to understand if that is within the capability for the regulators for the helicopters. As we understand, the helicopter pilots feel very comfortable with this, but it's not. Because it's quite a regulated environment. This needs to also be taken into account. So, kind of wrapping up on minor interventions, we don't see significant barriers. There's some differences, but nothing, no showstoppers. On the major intervention side, this is where we see a few more challenges and new approaches coming in, and kind of well, I would say 1 and 2 are the main options, and then 3 is a slight different approach to tow to port. So I'll run through these, and probably critical at this stage is that at least as far as I'm aware, no major interventions have actually been executed at this stage. So similar to what I was saying at the beginning in terms of turbine failure rates, it's probably a good thing from a failure rate point of view that nothing's happened, or that there has been no major failure rates. However, it does also mean that we haven't seen these operations being undertaken yet. So as I mentioned, this major intervention is something like a blade, gearbox, or a powertrain component needing to be replaced. So these components are at the hub height and are quite large, heavy components. And just kind of giving a sense of scale, so 10 megawatt kind of current generation turbine will have a hub height of greater than 110 or maybe 120 meters. So at those heights, a small motion and a small amount of pitch or roll will create a lot of lateral motion at the nacelle height, and that needs to be if it's been done lifted with a crane vessel, that needs to be compensated by the crane, and it's quite a challenging environment because of you're at that height, and there's also quite a significant reach to get to the center of the tower. And what we see is that although there are oil and gas vessels with quite significant capacity or weight carrying capability, they've been designed for that purpose and not for the purposes of height and reach. So actually the components, relatively speaking, are light in floating wind or offshore wind, but just more awkward based on the height and reach compared to oil and gas. So the vessels that are available aren't as suitable for the task. Then if you look at the second method is the tow to port, and this is where floating wind is unique in allowing an option to disconnect your platform and tow it back to shelter or back into port. And what this the big advantage of this is it brings you into a more controlled environment, and also you don't need to use the much higher cost jackup vessels or heavy lift vessels than you would have to alternatively. What it does, however, mean is that it puts the bottleneck down on the onshore ports and the infrastructure that you have near to the project or in the vicinity of the project. And then, this particularly becomes challenging when you're talking about a very large project, or if there are multiple large projects in the area, that there becomes competition for space to service these projects. In addition, the plug and play systems of electrical and the mechanical disconnection for your power cables and your mooring lines to connect to the seabed are still very much in development. So yeah, there's again advantages, but some risks there with the in development technologies. And I just thought I'd also kind of put in the option of the towing to shelter. So this meaning you're bringing not back into port, which may be a lot more users and more competition for space. But if you can have an area where it's more sheltered, it increases your operational windows by bringing back nearer to shore. You're not as exposed to the harsher weather, but also it brings you into shallower water. So then you could potentially use jackup vessels to do the operations. And jackup vessels are very sensitive to water depth because the deeper the water, the less height they have the platform can elevate. So the bigger the crane there needs to be. So in bringing to the shallower waters, there's quite a benefit to increasing their height. Of course, this challenge it's very much dependent on the bathymetry or the water depths in the area that's available and the sheltering that's available, and also if there's any permitting requirements to do these operations. But it does alleviate the port bottleneck. So these are kind of a couple of the strategy, kind of leading strategies for the major interventions. And as we get to the future O&M challenges, just outlining a key kind of building on what's been mentioned. So first one being the turbines are getting much larger. And this is one of the key drivers to making cost competitive. But then the challenges from an O&M perspective, that the components themselves, and particularly the nacelle height, is getting larger. So the problems I mentioned previously are exacerbated, and there's again, there are no vessels that can do these 15 megawatt O&M lifts at the moment. So it's the approach to how these are going to be done. You can see that the picture at the top right is that's the Saipem 7000, so one of the largest heavy lift vessels in the world, and that's lifting there. You can see the Siemens 6 megawatt turbine. So relatively speaking, that's a small turbine, but you can see there's not much margin there. And as mentioned, kind of as we go to bigger projects, we're going to deeper water to get that space, which generally tends to see both harsher weather conditions and the longer distances to port. So it makes the operations and the logistics more challenging. And mentioning logistics, we have limited track record, so it's key now also proving the solutions. With kind of the current limited track record, and particularly we see challenges around if the serial component exchanges. So if you're, for example, having to replace all blades on a project, how would that be undertaken? And either from doing the work offshore or bringing the platforms back to port, there's quite significant logistics in undertaking that. The health and safety considerations, again, there's track record from offshore wind and experience, as well as oil and gas, but where there's some synergies, but there are still some gaps. And we see also not the regulations. Again, there's gaps in those. So going forward, understanding the gaps and developing new guidelines to fill those is critical to undertaking good operations. And from subsea assets, critical to both monitor and inspect, because there's a lot of critical to the asset integrity, particularly on the platforms, mooring lines, and the anchors. These need to be kept in good condition and understand when any replacements or maintenance is required. And additionally, dynamic cables need to understand if there's likelihood of failure. Although they are not critical to the asset integrity, they are to power production. So I just wanted to highlight some of the kind of where these future O&M opportunities and innovations to tackle some of these challenges, and this is by no way a kind of exclusive or all the technologies, but it's just a flavor. As I mentioned, on the heavy lift vessel side, the designs are for the vessels that have been used to date are oil and gas designs. We do see some designs now coming through more bespoke to offshore and floating wind, particularly driving the requirements for sufficient height and reach, but also looking at things like the stability of the vessel and damping or compensating systems to undertake those quite challenging lifts. So you can see examples of the offshore wind logistics vessel. Also, there's some supporting technologies around the crane systems and the approach to doing that. So yeah, ways of dampening, compensating the motions on the actual tool themselves. So rather than the whole crane dampening it, you have the damping done on the at the lift. Then also looking at kind of another angle to doing the work offshore is actually these technologies to lower the components down before the transferring onto the vessel to make that component replacement. So these are, again, are just a few examples. Critical to bringing down is when you have pitch and roll motions of the platform. The lower you can get that, the lower the motions are and the easier the lift becomes, as well as needing smaller cranes. So there's just an example here, for example, of some climbing cranes, so cranes that actually climb up the tower, systems without cranes, so using systems of wires, and then kind of a hybrid crane climbing system, so you kind of have a joint system that works together. So and creates, but by having that connection, it creates a compensation system. On as well, also on the tow to port side, there's some interesting technologies and innovations coming through. Again, just a kind of a snapshot of these, where we see the opportunities around the array cable connection, disconnection, also the mooring line connection, disconnection. So these are enabling technologies allowing or facilitating the taking the platform off site, off location, back to shore. And also critical is not only the disconnect, it's taking the tension off the mooring lines and then retensioning those. And also, of course, the onshore logistics required in construction, but also in O&M potentially, you're going to require some lifting potentially. And there's just an example of a few of those on the right. So the first subseas, the ball grab system, the step adjuster mooring tensioning system, and tug docks, they have a docking system. So these are a couple of ideas that and technologies are in development to support the some of those key O&M challenges. So that wraps up my session. Really just to give a flavour of the floating wind O&M status at the moment, as well as the kind of key challenges and how those challenges are being considered for the future commercial scale projects. Thank you very much for your time.